I think first I should already thank the audience before I begin my presentation. It's been a long day, and I hope I can make it worth your time. So coming to my talk, it is about delayed fracture susceptibility of 1.5 gigapascal class dual phase steel, which we evaluate by U-bend test. So jumping right in, U-bend test is a very simple test where we make the sample into a U-bend, and then we tighten it with a bolt and a nut. And the stress of here depends on the tightening of this bolt and nut. And then we charge it electrochemically and we observe if there is any fracture. Here is a very small snippet. You can focus on this area where there is this red arrow, and you would see there is a crack which is being initiated. And then there is fracture. I think this snippet already tells us how catastrophic such a delayed fracture can be if a material is in service. So therefore, it is important to understand the delayed fracture behavior and avoid it. So normally we always study the effect of hydrogen concentration, which we vary the charging conditions, and then of course the stress. In our case, in the U-bend sample, we change the bolt tightening conditions. But in automobile steels, most of the steel parts are formed, which in other words, there's already some deformation before they're in service. So it's also important to understand the effect of strain. In the U-bend test, there's an advantage that we can change the bending radius and achieve the influence of strain. And then to top it off, we study the microstructure to understand the micromechanisms of these three factors on the delayed fracture. In the current presentation, however, I'll restrict myself to a radius of 10 millimeters. So the DP steel which I investigate has ultimate tensile strength of about 1.5 gigapascals, 25% ferrite microstructure. In this work, I also compare with a tempered martensite of the same composition but a different heat treatment, which also has nearly 1.5 gigapascal ultimate tensile strength. So the U-bend test results for the DP steel, first we charge it in 3 weight percent NaCl, 0.3 gram per liter NH4 SCN. We first charge it with a current density of 1 ampere per meter square for 12 hours, and if there is no fracture, then we increase the current density to 10 ampere per meter square, and then we see. Here are the results. In the current talk, however, I'll focus on this particular condition where we have an applied stress of about 1500 megapascals and a current density where it fractures at a current density of 10 ampere per meter square. There are two important reasons. The first reason is, of course, the UTS is about 1.5 gigapascals. And secondly, the more important reason is when we studied the tempered martensite, it fractured for 1500 megapascals, but already at a current density of 1 ampere per meter square. In other words, for the dual phase steel, we see that the delayed fracture resistance is enhanced. Therefore, this condition is quite interesting for us. So before I get into dual phase steel, I wanted to talk about two important aspects of delayed fracture in tempered martensite. So normally we need to first study the crack initiation and crack propagation. So in tempered martensite, the crack initiation was always observed at a subsurface level. So the reason for subsurface crack initiation is simple, that when we have a U-bend sample, this is a 3-point bending test, this is a pin, and when it is relaxed, there is a compressive stress at the surface. And this is finite element simulations of tempered martensite. -1 corresponds to the top of the U-bend sample and plus corresponds to the bottom. And for the applied stress of about 1000 megapascals, we can see that the stress at the surface is quite less. In fact, the highest stress concentration is not exactly at the center, but very close to the center. So now when we charge it with hydrogen, the hydrogen diffuses to this highest stress region, and therefore we have a subsurface crack initiation. And the second aspect is the crack propagation. In tempered martensite, we have always seen that the crack propagation is at about in the prior austenite grain boundaries, which we verified using the ARPG software. So crack initiation is subsurface and crack propagation is along the prior austenite grain boundaries. Now moving on to the DP steel, we observe that we see a competitive cracking behavior. So this is a fracture sample and the cross section. Here we see a subsurface crack, very similar to what we have seen in the tempered martensite. However, when we look at this region a little more closely, we see that there is a subsurface crack which is propagating from the surface to the from the center to the surface, but also there is a surface crack which is propagating towards the center. And eventually what we see is both these surface and subsurface crack coalesce. Now we confirm the same. This is a tilted sample where this is the cross section and this is the surface, and we can see very clearly that higher magnification, that it's the surface crack which will propagate towards the center of the specimen. So then we ask, why does it happen? It didn't happen in the tempered martensite. So we took a step back and we looked at the tensile specimen, because in a U-bend sample we can approximate the surface condition to be very close to the tensile condition. And then firstly what we observed was void formation at martensite ferrite interface, and also void formation at manganese sulfide inclusions with ferrite and martensite, and some nano voids in martensite. In addition, we have also seen ferrous-austenite grain boundary martensite cracking in the tensile sample. Now, when we went back and looked at the U-bend sample, this is before ball tightening and before hydrogen charging, we already see the presence of some surface cracks. And at a higher magnification, so when we look at the cross section, the cracking is evident. So when we look at higher magnification in ECC, electron channel contrast imaging, firstly, we see the void formation very, very similar to what we have seen in the tensile studies. And also, of course, we see the cracking, which was very similar to the tensile studies. So now we can understand that when we charge it with hydrogen, these pre-existing cracks will grow and cause surface cracking. So now in the DP steel, we understand competitive cracking, that is the formation of a surface crack, and a subsurface crack, which is similar to tempered martensite. So the next is to understand the crack propagation. So here, first I show, so in the U-bend sample, as I have shown earlier, it is important to realize that the stress conditions are different across the different points in the cross section. So first we study the subsurface crack, and this is the crack tip. What we see is that the ferrite is arresting the crack, and this is the ECC micrograph of the same region, and we can see that the ferrite is actually arresting the crack. But another very interesting thing is that the crack does not propagate along the martensite ferrite phase boundaries, or in other words, there is no hydrogen enhanced decohesion mechanism, which is normally reported in DP steels in terms of hydrogen embrittlement. And the ferrite arresting the crack is also evident here in these green arrows, where in two regions we can see that the ferrite is arresting the crack. And when the ferrite arrests the crack, we can see the fresh crack forms at the ferrite martensite interface, and the crack propagates. Now we can also see in the CAM map here that between these two cracks there is localized plasticity, and we confirm the same with studying the sample in ECC. And we can see here, this is basically the ligament between the two cracks, and we see something which indicates localized plasticity, very similar to shear band formation, and we did not observe any voids. So we can also confirm that the crack coalescence happens through the localized plasticity. So this is regarding the role of ferrite in the crack propagation. Now when we studied the martensite, we observed a quasi-cleavage fracture, and the cracks propagation was along 110 plane, and this is actually very similar to what many other studies have reported in context of martensite steels. And now we go to the surface crack. So this is the surface, and we look at a surface crack, and in surface crack, interestingly, we observe that the crack propagation mechanism is almost the same, not almost, exactly identical. Here there is a ferrite which arrests the crack, and there is, in the CAM map we can see that there is a localized plasticity causing coalescence of the cracks. And then when we looked at martensite, we saw quasi-cleavage fracture again, with the fracture propagating along 110 planes. So to summarize, in tempered martensite we only see subsurface cracks. However, in the dual phase steels we see a competitive cracking where we see both surface as well as subsurface cracks. And when it comes to the crack propagation, in the tempered martensite, it was predominantly along the ferrous-austenite grain boundaries. However, in the DP steel, firstly, the ferrite acts as arrests the crack propagation. Secondly, there is no HED or phase boundary decohesion which was observed. And thirdly, when we studied the martensite fracture, we observed 110 quasi-cleavage fracture. Thank you.
Thank you for that talk.